Our next presenter is Niloofar Shadab. She's currently a PhD candidate in the Department of Industrial and Systems Engineering at Virginia Tech. Her research focuses on systems engineering of intelligent systems. She received her master's from the University of Maryland at College Park and her bachelor's in aerospace engineering from Sharif University of Technology. Niloofar will be presenting her work, Engineering Intelligent Systems, a Systems Theoretic Perspective. Niloofar, are you able to bring up your slides?
Hello. I'm sharing.
Perfect. Looks good.
So
Can you go in,
okay.
Can you go into full presenter mode? Excellent.
Okay, thank you so much for your introduction. Hello everyone. I'm Far and I'm presenting my research on systems engineering of intelligent systems under the supervision of Dr. Peter Billing. So before going to the presentation, I wanted to show you the research roadmap that I considered for my PhD research. Basically, this research can be broken down into three different parts. The first part is to investigate why we need a new paradigm for systems engineering of AI-centric systems or intelligent systems. For that, we need to take a look at if and why we need a new category system for intelligent systems, and if there's any limitations in the current systems engineering practices. And then I'll, with the introduction and of the paradigm shift that we propose to address such limitations in current systems engineering practices. So basically, I will focus on the closed system paradigm that I'm going to talk about next. And in the final stage of my research, I will be talking about what will be the focus of my dissertation, which consists of mainly the engineering implications of such a paradigm. So having said that, I'm gonna start with the discussion of why we think intelligent systems should be considered as a new category of systems. So historically, systems engineers came up with new category of systems when they encounter with some new properties that they cannot explain using the available categories. So as a result, they started with traditional systems, and then they introduced socio-technical systems to incorporate human factors and human behaviors of complex systems. And then they came up with system of systems that include um, a number of complex systems that interact with each other to achieve a higher goal. So we argue that intelligent systems should be also considered as a new and separate category of system because of the new properties that intelligence brings to these type of systems. And I'm gonna talk about one of the main differences that this type of system has um, between this type of system and the traditional systems. So in traditional systems, we have this huge assumption of exogenous evolution, and we assume that the system does not have any kind of endogenous evolution, except for some degradation over their life cycle, which are mostly predicted, and they cannot be considered as endogenous evolution of their behavior. As a result, all these current systems engineering activities, such as the modeling processes and the verification of strategies, rely on this assumption. And for that, they create these homomorphic images of the system to use for design purposes or verification purposes. And we have this assumption that this parameterization and this set of homomorphic systems will not change, and it's a finite set. On the other hand, endogenous evolution intelligent systems provide a different view for these systems, because in this case we no longer have homomorphic set of images that don't change over time. So instead, we have this possibility to create the homomorphic images of the system of interest, which leads us to the conclusion that we lack the knowledge of the complete set of homomorphic images for the purpose of verification and design for such systems. And this means that maybe the current practices are not sufficient for this purpose. And even if we consider that we can create a dynamic and evolving images for SE practices, we can come up with some new sets of problems and issues, such as recursion or computationally complex solutions. As a think that we need a new paradigm for systems engineering of intelligent systems. Having said that, I'll go over the definition, the system's theoretical definition of open versus closed systems engineering before going to the introduction of this new paradigm. So basically, the open systems engineering depends on the input and outputs relations. So in this open systems engineering, we drive requirements from inputs-outputs relationships, and then engineer functionalities to meet requirements and provide desired outputs. Therefore, we can verify the relation between functions and requirements for the system by testing the inputs and outputs. In contrast, closed systems are based on the need versus outcomes. So we are working with outcomes instead of outputs, and we're working with needs instead of requirements. So as a result, we need to derive needs from relations between the system and context and the problem space. And then consequently, we need outcomes to meet systems needs. So in this case, we need to verify systems need outcomes relations instead of requirement function relations. So this is the main difference between systems engineering. So one of the main that we have that led us to a conclusion that we need closed systems engineering is a fact that we believe that intelligence is a global phenomenon. So the main contribution of my research up to now is that intelligence is a global phenomenon. How did we come up with this conclusion is working with the relations between intelligence and learning concept. So we considered all abilities of this relation. So first off, we assumed that intelligence could be a property of the system. And if we consider intelligence as a property of the system, then learning could be either a consequence of this property or the representation of this property. if we consider learning as a consequence of this property, we need to do direct engineering to engineer intelligence property. For that, we require a specific definition for intelligence, and we need to be able to characterize intelligence, which are currently unavailable because there are not a universal definition for intelligence. Each field has their own definition, and as a result, we cannot, as systems engineers, characterize property properly. So then we switch to the next possibility. We can consider learning as a representation of this intelligence property. But in this case, we can do indirect engineering. In fact, the current engineering practices focus on this approach. But even if we do this, then in this context, we need to consider learning also as a property of the system. And this means that both learning and intelligence are independent of the context. So this is the final conclusion, that intelligence is considered a local phenomena, which can be relegated to a subsystem. And we believe that most of the problems and bottlenecks in the current practice of AI engineering relies in this assumption for intelligence and learning. So we propose a new definition for intelligence. So we propose that intelligence is a property of the system's relation to context. If we consider this definition, whether learning is a representation, the is that both are embodied in the context. So which means that intelligence should be considered as a global phenomenon. If intelligence is a global phenomenon, then we can kind of derive the closeness property of this global property. When we want to model the highly and tightly coupled context and system, we need to consider that all the outputs of the system should be also the inputs to the system to capture all these dependencies. So you can see that here we cannot model it just by the input-output relations here. So as a result, rationally distinguishing an intelligence systems context as being part of the intelligence systems itself requires adopting the closed view. So what we mean by closed systems engineering in like the formal definition of closed systems engineering, as I said in the previous slide, to capture this with the context and system, and distinguishing the context as part of the boundary, we need to consider all the outputs as all the inputs to the system, which is the highest level of abstraction for the system compared in relations to context. As you can see in picture A, the absolute open system is shown, which don't have any intersections with the outputs. So we can model the inputs, the system's interaction with the context only by these relations. And the picture B and C and D are all to some degree closed and to some degree open. They use feedback loops, and they might use outside systems to make sense of the inputs and outputs of the system of interest. But at the highest level of abstraction, they are still open systems because they can be modeled that way. So we propose a new definition for these closed systems engineering, which is a little bit different from the feedback loop closed systems. But how to enable such a systems engineering paradigm? We decided to use the concept of variety. So in cybernetics, this concept has been very widely, specifically Ross Ashby used this concept extensively to address some of the behaviors of complex systems. And he has this law of requisite variety. I'm going to talk about here, but we're going to use it for this research. But the bottom line for this concept is that varieties can be divided into two forms. We have bounded varieties, the first form of variety, which are invariant to changes in context. And the system needs to maintain these bounded varieties within their boundary in order to preserve the core characteristics of the system. On the other hand, the unbounded, which is the new addition to this engineering practices. The unbounded variety is not invariant to changes in context. So with this unbounded variety, we can actually enable this coupling with the context. So as you can see in the picture, this way we can see that open systems engineering practices and closed systems engineering practices could be the complementary approaches to develop a true artificial intelligence systems. So as you can see, a variety of contexts can enter to the system's regulator or control system, and it is responsible to maintain those bounded varieties, and as a result provide desired outputs. On the other hand, the unbounded variety, in line with the desired output, is responsible to provide the desired outcomes in relation to the context. So we want to argue that with this idea of varieties, we can achieve the most general form of scalability of intelligence. Scalability is achieved by only scaling up the bounded varieties, which is one form of scaling intelligence. So basically, they focus on the inputs and outputs, like the number of queries per second or the number of users. However, we can also have unbounded varieties, and we need to be able to scale up these unbounded varieties as well to scale up the outcomes of the intelligence system. For example, survival in new contexts. So we can conclude that with the scalability of unbounded varieties in context, scaling systems' bounded varieties will be insufficient at some point, and at some point, scaling the variety of an intelligence relies predominantly on closed systems phenomena. So now, the next focus of this research would be the development of this new paradigm to encompass this closed systems engineering and the concept of variety. So for this purpose, we want to use the core and periphery concept to achieve a new form of hierarchical systems structure whose focus is beyond physical hierarchy. This core and periphery has two parts. The core responsible for engineering, for maintaining and the bounded varieties in the system, which would follow an open system paradigm for engineering it. And in addition, to engineer an unbounded variety, we need to engineer a periphery that would follow a closed system paradigm. So as a result, we believe that adaptation to changes in context involves the interplay between the core and periphery. This means that the adaptation of intelligence systems to changes in context is principally a closed system phenomenon that starts from when it receives some unknown uncertainties and unknown shocks, and it will result in open in the core while maintaining the bounded varieties of the core and maintaining the most important core characteristics of the intelligence system. So the next step in this research is to identify the required properties for such a closed intelligence systems. Some of them could be the novel properties that has never been presented in any current. So you can see in the picture that there are some possibilities for having these types of properties in systems. Two of them are specifically of my interest. One is the antifragility property, and the second one is the survivability, because they are going to be some new properties that systems engineers have never been working with. So engineering antifragility would be one of the main concepts in systems engineering of intelligence systems. First off, we need to say that we need to define antifragility. Antifragility is not the opposite of fragility. Fragility's opposite of fragility is robustness. So in robustness, when we say that a system has robustness, it means that it can be stable when it encounters with some shocks from the outside. But antifragility is one step further. It says that the system not only can survive from those shocks, but also it can learn and grow from those shocks. So it's not stable as the way that a robust system is when it is learning from those shocks. At least at the end, the system will get a new equilibrium using these types of properties. So we believe that to engineer the periphery part, we need such a property, because to engineer this part, we cannot rely on optimization problems, because we're not looking for a specific answer that optimization. We're looking for a satisfaction problem where an input associated with an answer enters the system, and system can survive and tolerate those inputs and uncertainty. So as a result, we think that we need a probability distribution of outcomes for the system, which is resulted by the variance coming from this distribution, probability distribution of uncertainties. And each outcome has a specificity, and we can define antifragility as the ability to modify a specificity function. So we need to formalize this definition And this is the current focus of my research, or the future focus. Um, the next important one is the survivability. So in order for the system to survive, it should stay in the convex region of its behaviors and states. In the presence of unknown uncertainties and antifragility property, systems needs to be able to divert from or halt their normal operations, and as a result, it should exist some possibility where the system redirects to a safe survival state. So survival state should be an addition to the set of system states, and the focus here is near such a survival state, how this survival state can block all the information from entering to the core while encountering with unknown uncertainties. So there are some other implications in systems engineering practices that we will work on for the verification and validation. As I talked about, current practices focus on verifying the system in the testing environment, assuming that the inputs and outputs will remain the same in the operating environment. We believe that closed forms VNVs would be complementary to the current open forms VNV, and we want to work on that to address these limitations of the current approaches. The other two important practices in systems engineering that we want to focus on is the reusability practices. When systems engineers use ICDs to enable one system from a context to another context. So maybe we need a new form of reusable intelligence systems that need to be engineered away from wrong couplings with their context. And also, we need to be able to translate the function requirements from one context to another, to being able to translate needs and outcomes from one context to another one. The other important one is systems manufacturing and maintenance practices. So in order to address the closedness and endogenous evolution of such systems, we need to examine whether the current settings, like a product line, would be a suitable setting for manufacturing or maintaining such systems, or we might need to new settings such as product herding. So that was all. Thank you for listening.
Niloofar, can you see the questions?
Sure. You have made a case for defining a new category of system. What class of systems do you think best aligned with intelligence systems? Well, that's a really good question. I mean, we cannot be the possibility of using this category of systems and use intelligence system as a subcategory. But the problem is that we want to point out that we are working with artificial intelligence. So when we want to add a new subsystem of to system of system, then how would you differentiate biological intelligence versus the engineered intelligence? So we think that for the properties of intelligence, it's engineered intelligence. It's better to consider them as a new category, because it not only has some different properties to itself, it also requires new approaches for engineering, for systems engineering. So yeah, I hope that I answered your question.
I typed in myself an additional question. And so in some ways you can view this as a relationship between the output and the outcome. And the question is, can you predict the possible outcomes, or at least
Well,
bound them at least?
yeah, I mean, there, as I mentioned, the requisite variety, the law of requisite variety can provide some lower bounds for predicting the possible outcomes. So Ross Ashby has this rule of only variety can destroy variety for his law of requisite variety. So there are some bound um, some lower bounds for this possibility, and also for the upper bounds, we need to focus on the expansion of the closed system. So the closed system needs to be bounded at some point, needs to be closed at some point, um, go outward for for forever. So I'm not still working on that part because it's so advanced in this research, but these are some possibilities that we're looking for to bound the possibility of outcomes for intelligent systems.
Okay, I think you have one more question here.
Sure. Thank you for, you're welcome, thanks. Are satisfaction problems different from? Well, the satisfaction problem provides a a set of possible solutions for the system at 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 a single time, right? So stochastic optimization, I'm not really familiar with those stochastic optimization processes, so I'm not sure if they include this assumption as well. But in a satisfaction problem, we have this tolerance function for the system based on each uncertainty. And the only assumption that we have is that the combination of uncertainties and inputs to the system will not pass that tolerance function. I'm not sure if the stochastic optimization has this assumption to it. But yeah, I don't know if I answered your question. And Danny, thank you. Thank you.
Good.
All good here. Thanks so much, Niloofar.